In this video, I want to talk to you a bit about the ambiguous case. In geometry, we learned that to prove two triangles are congruent, we can use side, 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 angle, side, angle, side, angle, or angle, angle, side. We also have the possibility of a hypotenuse leg situation. But what we determine in that course is that angle, angle, angle doesn't necessarily produce congruent triangles, but it does produce similar triangles. But we also learn that angle side side isn't useful in either congruence or similarity. So the question naturally becomes, why not? What's so wrong with angle side side? Today I want to introduce you to this ambiguous case, which is the angle side side situation we were just referring to. So what I've drawn here is an angle measuring 30 degrees, angle A, and I've got a side C that's 8 units long. Now what we're looking at here is a triangle ABC, so there's some point C somewhere along this dashed segment that's going to complete the 3 vertices for this triangle. Now I know that wherever that third side of that triangle lies, could be here, for example, that this side of the triangle is what we'd refer to as a lowercase a. It would be the side opposite angle A. And here I haven't given that side a measurement yet, because depending upon what type of a measure I give it, we're going to see some different things occur. So we're going to be looking at, with the use of my handy dandy compass, we're going to be looking at what happens as this side opposite angle A changes in length. So the first length that we want to look at is a length of 3 units. Okay, so I'm going to set my compass up here to 3 units in length. And I'm going to put my pivot point then on point B. And wherever this intersects this dashed segment would be the location of point C, because I know that would have to be 3 units away from point B. And we can see in this case that there's a dilemma, because this never reaches that segment. It's just simply too short. So when A takes on a value like 3, well, we have a problem. It doesn't create a triangle. Well, let's go a little higher. Let's go with a length of 4 and see what happens. Okay, so when I set my compass at a length of 4 units in this case, put my pivot point back on B, then we can see that it does hit that segment, specifically right down here. There's one point where it's going to reach that dashed segment, and let's go ahead and mark that. Put my pencil out here. I'm going to hit right there. Okay, so if I were to put point C here at this location, then I know that this segment BC, which we call segment A, would have a length of 4 units. So let's just take a straight edge here, and we're going to draw in that segment. We'll come back to that segment. So in this case, when A is 3, it was too short. When A is 4, it's just right. What happens if we go a little bit higher and go to 5? So we're currently at 4. We're going to go up to 5. Now, I'm going to take a minute. Think about what you think is going to happen here. Compass is being contrary. Okay, so I'm going to put my pivot point on B again. And now watch what happens. Hey! Magic! Cross the line right there. Just barely see that pencil mark, but there'd be an intersection point right here. The problem is, there's also an intersection point over here, which means when side A has a length of 5 units, then I have 2 possible locations. I have one location here, so that this length is 5 units long, and I have another location here. Keep in mind, in each case, we'd have the same 30-degree angle. We have the same side C in this case, that would be 8 units long, and then here or here produces a side opposite angle A, which is that side A with length 5. And that's why we refer to it as the ambiguous case. Depending on what your measurements are given, you could either end up with no triangle possible, which is what we saw when a equaled 3. When a equals 4, there was exactly one triangle possible. But when a equals 5, there are 2 triangles possible. And that's why it's called the ambiguous case. It's ambiguous because we don't quite know what we're going to get. Now, we have some ways that we can reason through determining which of these 3 outcomes would be possible. But it does illustrate why we don't say the triangles are congruent. For example, if we consider the triangle, let's call this C sub 1, and let's call this one C sub 2 for a minute. We're going to ignore this 4 momentarily. So I have 2 triangles here that would have side of 8, side of 5, and then this non-included angle of 30 degrees. In this triangle, ABC2, I have a side of 8, a side of 5, and a non-included angle of 30 degrees. So by general description, those 2 triangles have the same information. 2 side lengths and a non-included angle. 2 sides, non-included angle, same 2 side lengths, non-included angle. But it's very clear that the triangle ABC1 is not congruent to triangle ABC2, nor are they similar. So this ambiguous case doesn't fall into congruence in geometry, and it doesn't fall into similarity in geometry because neither of them apply. Now let's go back to that 4 for a minute. Why did this length of 4 work? Well, let's kind of go back to right triangle trig. Let's call this X for the moment. We know that that side X, if I consider this A, B, let's just call this point, let's call it C sub 3. In triangle ABC sub 3, we know this side, BC3, which we called X, is opposite the 30. And we know that this 8 in that triangle represents the side opposite this angle. The distance from a point to a line, the shortest distance possible, is the length of a segment that is perpendicular to the line, which means this triangle ABC3 is a right triangle. It also describes why these 5s work on either side of it. They become basically new hypotenusae in each of these other 2 smaller triangles. But that 4, now in that right triangle ABC sub 3, lies opposite the 30 degree angle. Now in a 30, 60, 90 triangle, which is ABC3, the side opposite the 30 degree angle is half as long as the hypotenuse, which is why this 4, which is half of 8, produces exactly one triangle. Anything less than 4, like we saw with the 3, would be something that would be too short. For example, this type of segment. Anything greater than that 4 becomes another hypotenuse in another triangle where this represents the height, this represents one of the base maybe, or one of the other pair of legs, but we get these other hypotenusae that come into play. So there are some criteria that we can start to look at to determine when that ambiguous case is going to produce one triangle, when it's going to produce no triangles, or when it's going to produce 2 of them. So let's kind of discuss that in more generic terms. And to do that, let's draw ourselves just kind of a generic diagram. So with that in mind, I'm going to give ourselves a segment and some angle measure. I'm going to draw it as a cube, but this is going to apply in other situations. Okay, so let's assume that this side is much like what we saw in the dash segment in the last diagram. This is our side A, B. Now we know along this dash segment, I'm going to make it a little bit longer since I drew my B out so far. There we go. We know somewhere along this segment is the length that's going to be perpendicular to that segment. So let's kind of draw that in, just kind of dashed. There is some distance between point B and this side AC that's going to be perpendicular to it. So let's say that this length here, which is going to be the length of side C, is given. So we're going to assume that you're given the measure of angle A, the length of side C, and the length of side A, just like what we were given in the last one. Okay, so what we've determined, let's call this measure of angle A, we're going to refer to that as theta. Okay, so if I want to determine that scenario under which there is one solution, let's call this point D for a minute, then the one solution has to occur where this segment BD is perpendicular to the segment AC. Now, because it's got to be perpendicular, we can fall back on what we know about right triangle trig. So from right triangle trig, the sine of theta would be the length of segment BD over the hypotenuse C. Now remember, this theta is given and that side C is given. So the length of side BD in this case would be C times the sine of angle theta. That would tell us how long this vertical segment is between point B and the side AC of the triangle. So what we learned in the last part is the criteria for A is based on the length of this segment. If A is too short, we're going to get this thing that's just this nubby little segment that doesn't even connect to segment AC. If A is exactly this long, then we get exactly one triangle. And if A is longer than that, then we have to compare and kind of think about. So if the length of side A is less than the length of segment BD, which is what we saw with the length of 3 in the last diagram, there is no triangle possible. You'd end up with this funny little nubby little shape, something like this, where it wouldn't connect. If the length of side A is equal to the length of segment BD, there is one triangle possible. Specifically, that's going to be your right triangle. Okay, so let's consider what happens if A is greater than BD. And that really depends on whether A is greater than BD, but how does it compare to the length of this side? If we choose a number that is between, it's less than C, but it's still greater than this number. So if AD is greater than the length of that height, BD, but it's less than C, that's where we get two triangles. Now, in the last example, we looked at a length of 5. The height in the triangle was 4. The side opposite, or the third side, side A, had a length of 5, and the length of this segment C was 8. So we had 4, 5, and 8, which is why it produced two triangles. Now, if this other side becomes greater than side C, then there's only going to be one triangle possible. And the reason for that, let's flip back to our last example. If I choose a number like 10, for example, that's longer than 8, if it's going to be longer than 8, then that means it has to lie in some hypotenuse out here that's going to be pushing A further away from that point B in order to make this become a unit of 10. But then we're no longer including this angle of 30 degrees. So the only way I could use a length such as 10 would be to put it over on this side and make that triangle more obtuse. So what we're going to see is that if the length of this segment is greater than the height and also less than this side, then we can get two triangles possible. If A is simply greater than B, than this segment C, then there's only going to be one triangle. So if that third side is greater than the length of C, there's one triangle possible. Specifically, we're going to end up with something over here. And that explains then why this angle side-side case isn't useful when it comes to proving triangles are congruent, because we don't have any guarantee that it'll even produce a triangle, or that it isn't possible to get two completely not congruent triangles to begin with. In a later video, we'll talk about how we can use this ambiguous case to find the solutions under specific given information.